All right, we are talking about current density and conductors. I've got an example. Find the power absorbed by a cylindrical, hint hint, resistor that has a uniform conductivity. The voltage between the two ends is V, and the current through it is I. Now, I've also drawn the figure here, and you need to be comfortable in drawing that figure if it's not provided to you. So you'll see my figure. I'm going to use cylindrical coordinates. So I've got the cylinder oriented along the z direction, right? And I'm giving it a length, capital L, and I'm giving it a radius A, and then I'm going to let the voltage at the bottom be positive compared to the top. And in that way, then, the current would flow from bottom to top, and so the current density, J, in red, has these arrows coming up. And so the electric field, right, the electric field here only has a Z component. That is, actually, let me increase the size of this thing. Okay, so the electric field only has a Z component. And this is due to, again, my choice in orientation of the cylinder and coordinate system. So you can think that, yeah, the electric field, the electric field is not going to change versus radius. Certainly not. There's no reason why the inside is going to be stronger or weaker than the outside of the cylinder, and it's also not going to change versus angle phi. All right, but it is going to change versus z, again, because the potential at the bottom is higher than the potential at the top. Now, because the resistor is uniform, we know the strength of that field, Ez in this case, is just the voltage divided by the length, right? At any point along the resistor, that's the electric field, again, because it's uniform. And also because it's uniform, similarly, the current density is constant. And the current density is simply the current that's going through, right, divided by the cross-sectional area. I'm giving this thing a radius a, so the cross-sectional area is pi a squared, and this is, remember, a vector, and so the direction of J, again, current flows from positive to negative, and so the direction of this thing is in the positive z direction, like that. Okay, now you remember from a previous video that the power in a conductor, absorbed by the conductor, is the integral over the volume of J dot E. Okay, so now we just need to solve for this integral. All right, well, this is going to be a triple integral. I'll fill in the bounds in a second, but let's talk about the integrand. So I've got J dotted with E. So AZ dotted with AZ is 1, because it's a unit vector. So then I'm left with, and remember, EZ is V over L, so I'm left with I times V over pi a squared L. And then I need the differential volume element here, and we're operating in cylindrical coordinates. So that differential element is rho, d phi, dz. All right, now let's talk about the bounds. Well, rho in my cylinder is going from 0 to a, radius a, and phi in my cylinder, of course, we're going all the way around, so phi goes from 0 to 2 pi. And then finally, z, I've got the bottom of the cylinder on the xy plane. So z goes from 0 to L. So choose your coordinate system so that it's convenient. So by putting the cylinder at the xy plane, then z can start at 0 and then simply go to L. Okay, so I need to evaluate this integral. So first I'm going to do it versus rho. So I have this rho hanging around from the differential volume element, and then everything else is a constant, IV, pi, a, L. And so the integral of this thing is 1/2 rho squared times that constant. So this becomes z goes from 0 to L phi goes from 0 to 2 pi, and then IV, and then I pick up a half from the integration, so over 2 pi a squared L rho squared, and rho is going to go from 0 to a, and then I'm left with d phi dz. All right, so I plug in a for rho, and I get a squared, which cancels with this a squared, so that's nice. And then I plug in 0 for rho, and then I just get 0. So this is great. This is good for us mathematically. This works out very nicely. And so now I'm left with integral from z goes from 0 to L. Integral phi goes from 0 to 2 pi. And then I just have I v over 2 pi L, again because the a squared canceled with the a squared. And then I have d phi dz. Okay, so I look at my integrand again, and I remember that these things are all constant. There are no phis there, there are no z's there. And so now this is great. So we love this type of problem because the integration then, well, I take that constant and then I integrate that constant, and I pick up a 2 pi from phi, and I pick up an L from z, and lo and behold, the L's cancel, the 2 pi's cancel, and I'm left with I times V. That is the answer. And oh, I love this example. I really love this example because this, I'm going to put an exclamation point there. This is the result that you're told in circuit analysis, right? Your basic circuit course, that the power in a resistor is the I times V. You need a little bit of I, you need a little bit of V, multiply them together, and you have watts, you have power. And here we just used essentially Maxwell's equations, or electromagnetics, to show that result. The power is I times V. I love that. Also, I want to point out that our answer did not depend on the conductivity of the material, sigma. And again, that's because the resistor is uniform, but you can think of it in the following way. As the conductivity were to increase, then so would J, right? If the material is more conductive, then the current through it is going to be larger. So J would be larger. But if it's more conductive, E would decrease. The electric field would decrease because it takes less force less E to force charge through. So you've got J increasing, and then you've got E decreasing, and it happens proportionally, so that the sigmas would drop out, and what you're left with is J dot E it remains constant in this case. Awesome.